Greetings, this is Mr. Garwood with our continuing video series on Calculus 2nd edition by Briggs, Cochrane, and Gillette. Today we are starting section 2.6 on continuity, and I want to start with the definition of what it means for f to be continuous. If f is a function, we say that it is continuous at a if f sub a equals the limit as x goes to a of f of x. And this comes from the definition on page 80 in your textbook. Now, the textbook then gives us a really nice checklist, and that's what I want to focus on in this video, is the checklist for if a function is continuous. And it has 3 requirements. Number 1, f sub a is defined, which means that f sub a equals some number L. It has to be a number, though. It cannot be infinity. Requirement 2, the limit as x goes to a of f of x exists, which is another way of saying the limit as x goes to a from the left is the same as the limit as x goes to a from the right. And that comes from our definition from section 2.2. And the last thing on our checklist is the definition itself, which is that f sub a is that limit. You may recall from my video on section 2.2 that it was not a requirement that these two things be the same. It is not for the limit to exist. It is, however, for the function to be continuous at that point. So let's look at a couple examples. Our first example, I hope, looks familiar. We looked at this in our video in one of our videos on section 2.3. And it simply asks, is f continuous when x is 1? Well, we're just going to work through our checklist and make sure that it is. So the first thing on our checklist is that f sub a must be defined. It's got to be a number. So I'm going to look. My a here is 1. I'm looking when x is 1. So instead of that, we're going to say f sub 1 is defined. What is f of 1? Well, when x is 1, the function value is 1. It's defined. Check. Part 2 is probably the hardest part, and that's checking both sides of the limit. So part 2 asks that the limit as x goes to 1 of f of x exists. Okay? Well, that only works if, and I'm going to have to compute the left hand and the right hand limits. So the limit as x goes to 1 from the left, we're going to follow the top rule. So that's the limit x goes to 1 from the right of negative 2x plus 4. Well, no domain restrictions, so I can just substitute in. So I've got negative 2 times 1 plus 4, or negative 2 plus 4, which is 2. Now, I am hoping that already you're starting to see a problem, because that's 2, that's 1, not a good sign for continuity. But just so that we continue the process, so I've got the limit x goes to 1 from the right, f of x. Now for that one, I'm going to use the bottom rule. So that's the limit x goes to 1 from the right of the square root x minus 1. I don't think there's a domain restriction. We can check on the fly as we go, but I'm going to substitute in 1. That gives me the square root of 0, which is just 0. No domain restrictions, we're totally fine. Now, if I compare these two, we said that this exists only if the limit from the left and the limit from the right are the same. That is only true if that's true. Well, the problem here is they're not. So this fails. Condition 2 fails. No. X equals 1 is a point of discontinuity. Ran out of room. X equals 1 is a point of discontinuity. This fails because the limit does not exist. And if you remember that graph, this was that graph where things just did not come together. There was a big gap. So there's one that doesn't work. Let's look at another. So same kind of thing. We're going to look at this example. This is I used this example in that same video where I used the previous. So my key thing is f continuous at 3? So checkbox 1. F sub 3 has to be defined. Well, in the last one I had x equals 3 here, and I don't here. So what I'm going to do is I'm going to look for where's the equal sign. This is strictly greater than 3. This is less than or equal to 3. So I'm going to follow this rule. So f sub 3 is negative 3 times 3 plus 9. I just substituted 3 into the function rule here. Okay, well, as we've seen before, that's negative 9 plus 9, which is 0. 0 is a real number. We have no domain restrictions. This condition holds. Part 2 states that the limit as x goes to 3 of f of x exists. Okay. As we discussed before, the only way for me to check that is for me to look at the left and the right hand limits and make sure that they are the same. So I'm saying here that this is true if the limit as x goes to 3 from the left and the limit from the right those have to be the same. And I'm going to put a little question mark there because that's going to remind me that I need to check that they're the same. So from the left, I'm following this green rule. So I'm going to say the limit x goes to 3 from the left of f of x. Well, that's the limit as x goes to 3 from the left of negative 3x plus 9. Now, if I'm sneaky, I realize that these two things are exactly the same. That's negative 3 times 3 plus 9, which is 0. Now, so far so good. Both of those are 0. Now I've got to check from the right. Limit as x goes to 3 from the right of f of x. Well, that's the limit. X goes to 3 from the right of this rule, x squared minus 9. I'm going to substitute in and check as we go that there's no domain restrictions. So that's 3 squared minus 9. Square root of 9 minus 9. Square root of 0, simply 0. Now, hey, look. The left and the right are the same value. This holds true. The limit exists. Our last condition then, condition 3, is that f of 3 and the limit as x goes to 3 of f of x must be the same. Okay? Well, we just saw a moment ago that this is 0. This is 0. 0 equals 0. So these are the same. Thus, f is continuous when x equals 3. I hope you found this video useful, and I look forward to seeing you in our next video.